All right, so let's get started. This is NTU DB Theory Seminar number 4. Once again, welcome back. Okay. Today, we'll still be talking about ANN search, approximate nearest neighbor. Okay. So earlier, we have talked a lot about this. I'm sure at this point, everybody should have got much deeper understanding about this topic. Okay. And in particular, we have talked about a very popular method nowadays, and also a very simple and interesting and useful method for tackling ANN search, right? So this disk ANN method. So disk ANN is able to do how much space. So this is 1 over epsilon to the power of lambda, and then n, and then some polylog factors. And just so you know, this delta is the aspect ratio of your input, right? And furthermore, if you want to do query, and then this disk ANN is able to do 1 over epsilon to the power of lambda, and then some polylog factors again. Okay. All right. Good. So this is something guaranteed. All right. So that's the point here. Okay. Good. Now these are upper bounds. Okay, upper bounds in the sense that there are guarantees, right? So they are realized by a particular data structure, all right, such as disk ANN, right? So this is a guarantee, right? So if you want to prove an upper bound, then you are basically showing people, the problem is not too hard. You see what I'm saying? Okay, so look, I can solve the problem with these guarantees. So at least the problem will not get harder than this. You see what I'm saying? Okay, good. However, if you conduct this type of research, sooner or later you will hit your ceiling. You see what I'm saying? You'll come to a limit, right? Because you try to improve on these bounds, and then you will not be able to improve it endlessly, right? So at some point you will hit the wall, right? Okay, good. So when you do hit the wall, okay, so what's going to happen, right? The thing is, you don't know if you have hit a wall. You see what I'm saying? All right. So just like in the old days, right, for sorting, right? If you want to sort, let's say you do bubble sort, right? So wow, what a cool idea, right? So S squared, right? And then so that remained cool until someone came up with something n log n, right? But then n log n is already the lower bound if you talk about comparison-based sorting, right? But then that's the moment when you hit the wall and you have to basically convince everybody, hey, you know what? Do not invest any more time on sorting, right? So it's a dead end, right? So n log n is already optimal. So when we make such a claim, something's already optimal, right? Something, this is not improvable anymore. This is called lower bound, right? So basically lower bound showing that the problem is hard. You see what I'm saying? So for upper bound, you are showing the problem is easy, right? So no harder than this, right? But then for the lower bound, you have to show that the problem is hard. There is some inherent barrier sitting there preventing anybody from moving any further, all right? So this is the lower bound. So in general, which one is easier? If you want to prove an upper bound, is it easier? If you prove a lower bound, is it easier? Hard to say. Really hard to say. Okay, so lower bound is probably something you're not familiar with, but it doesn't necessarily mean that it will be more difficult. Okay. However, it's very important to think about the philosophy behind. Okay, so if you want to prove an upper bound, it suffices to show one algorithm, because that's your algorithm. However, it's very important to prove that your algorithm works on all data sets. These guarantees will have to hold on all data sets. That's the philosophy, right? That's the philosophy. That's the methodology. However, if you think about lower bounds, it's actually the opposite. Okay, so first of all, you cannot say, look, my algorithm, is n log n, and therefore everybody can do n log. We have to do n log n. The logic is wrong. You see what I'm saying? You can no longer make any conclusion based on just one algorithm. You see what I'm saying? You have to go for algorithms. Okay, not only algorithms that can be conceived by human beings, but also algorithms that can be conceived by aliens. You see what I'm saying? All right. So this is the type of argument you have to aim at. Okay. However, for lower bound, you don't really have to think about all data sets. You see what I'm saying? All right. For lower bounds, it suffices to show one data set that no algorithm can do well on. You see what I'm saying? So this is, if you think about philosophy, right? So very interesting, right? So this is exactly the opposite of upper bound analysis, upper bound research, right? So when you do upper bound, once again, you just have to give me one algorithm, okay? If you usually just give me one algorithm, right? You don't say, you know what, to achieve this bound, I can do this, I can do that. That's not what you normally do, right? So you just provide one algorithm. However, you cannot say my algorithm works well only on this data set, and therefore it's fast, right? And this is a fallacy, right? The logic is wrong, right? So you really have to say my algorithm works on all data sets. But if you want to prove lower bound, you have to go against all algorithms. However, it suffices to use just one data set, all right? So if you can show one data set, no algorithm can do well on, you have made it, okay? So today, we will start to talk about lower bounds. Actually, today we'll take a shallow look at lower bounds, right? So lower bounds really get to the barrier, right? So inherent barrier of this combinatorial optimization problem, all right? So I can tell you there's a lot to talk about, right? But today we will take a shallow look, okay? But not a trivial look, okay? I just want you to know that this area goes much, much deeper than what we're going to talk about today. Well, let's come back to these complexities, right? So as you can see, right? So it's very easy to come up with some criticism against these bounds, right? So for example, right? So you can see one potentially biggest criticism that people can come up with is, this lambda term there, right? So basically you can see that this is exponential dependence, right? So it implies that this thing will work only if lambda is small, right? So think about epsilon being 1/2, for example, right? 1/2. If epsilon is 1/2, and then this is basically 2 to the power of lambda, right? If 2 to the power of lambda, if lambda is something large, and then quickly this is going to dominate everything, right? So that would be the first thing we talk about, right? I think some time ago, I mentioned that, if this lambda is something unbounded, all right? So usually we say lambda is some fixed constant, all right? And in that case, then basically this term disappears if epsilon is some constant, and then everything would appear to be efficient, and this would be a plausible explanation of what's going on in practice about this KNF, right? So today, let's look at this lambda more carefully, right? So a very natural question is, what if lambda is large? Okay, what if lambda is large? Is it still possible to design something that's significantly better than the baseline? Still remember, there's a very tough baseline when it comes to ANN search, extremely, extremely tough, whose name is brute force scan, right? You simply calculate everything. You calculate n distances if there are n points, right? So the current time will have to be at least n, okay? So today I'll show you this is already the best you can do, unless you make an assumption about lambda, that a lambda is small, okay? So this is the first lower bound we're gonna discuss, all right? So let's get started, okay? Well, for that purpose, all I have to do is to show you one data set. You see what I'm saying? Okay, it's wrong to talk about any particular algorithm. You see what I'm saying? Okay, I cannot say brute force is slow, and therefore everybody will have to be slow, right? So that's nonsense. So I would not be talking about any algorithm. You can feel free to use whatever algorithm you can come up with, okay? And if you think that my argument does not work against your algorithm, I have failed, okay? So I'm going to construct a hard instance for you, okay? A hard instance, okay? So this hard instance goes like this. When we talk about a metric space, we have to talk about a ground set, right? So this is the ground set, all right? So I'm going to make this ground set, the size of it, m plus 1, okay? M plus 1 points. All right. So point is just a very convenient name. So I would rather call it elements. Okay. So because what they are really doesn't really matter. Okay. But by convention, let's say every element is called a point. Okay. And so I have got n plus 1 points here. You can choose whatever n is. All right. So the game works like you first give me a value of n, and then I construct the data set. All right. So basically, there is a hard input for every n. Right. So everything's fair and square. So now, say I have to design an input. Right. So this is just the ground set. You see what I'm saying? This is sort of like the universe, right? But I still have to give you the input. So as you would expect, the input consists of endpoints, right? So it doesn't really matter which endpoints, right? So the most important thing is only endpoints there, and then there is still another point that I can do something bad against your algorithm. Okay, good. So so you've got endpoints here. So let's say Q is the only point in M set minus this P. Okay, so there's only one point left, right? So that would be my Q. Okay, cool. All right, and then I give you the points. Okay, I give you the points, n points, right? But you don't get to see the Q. All right, you don't have the Q, right? That's not what we agreed on, right? In this problem, right? Okay, so I say, you know what? You have all the points here. Okay, so you can calculate. So you can calculate the distances among the points, right? So I also have to design the distance metric, right? I have to design the distance metric. So the distance metric goes like, if you take any 2 points, P1, P2, so these 2 points are from P, the points that you can see. You don't see the query point though, okay? You don't see the query point. So if you look at this, and then I give you 1 plus 2 epsilon. Okay, and epsilon is, this epsilon, 1 plus epsilon thing, right? We're talking about 1 plus epsilon, ANN search, right? Okay, so you first choose the value for n, you choose the value for epsilon, okay? And then I construct a data set based on n, based on epsilon, okay? So if you want, you can set epsilon to be 1, for example, okay? Or 1/2. 1/2 would be the better example here. Okay. All right, so now if this is the case, and then basically you can see that it's a very weird thing, something that you would not see on Euclidean points. You see what I'm saying? Okay, or you would see such kind of things when the dimensionality is very large. Okay, in other words, right? So basically, any 2 points that I give you, they are equidistant. You see what I'm saying? If you calculate their distances, they're always like 1 plus 2 epsilon. Except that I'm constructing an example in the metric space. Okay, I don't have to care about coordinates, right? Because in a metric space, it's more general than Euclidean space. You see what I'm saying? Suffices to give you the sets, suffices to give you the distances, and that's it, right? Okay, good. Now do whatever you want. Okay, feel free to construct data structures at this point. Okay, I don't care. All right, so you can do anything you want. Construct any data structure that you believe in, disk ANN, for example, okay, or brute force scale, up to you. All right, but when you say you are ready, let's play. Okay, so let's say you guys are ready. Okay, good. Now I'm your enemy, so I call myself an adversary. Okay, so I'm your adversary. Okay, so I want you to look bad, right? So I'm going to claim that no matter what your data structure is, and no matter how you plan to use your data structure to handle my query, I always have a way to force you to calculate n-1 distances. At least n-1. Okay, definitely n-1. So if this is the case, and then your query time cannot be better than n-1, let's say if you claim that your query time has a guarantee, say root n, right? And there's a contradiction, right? It's a contradiction, and therefore, basically sequential scale is the best, right? Maybe you can beat sequential scale by 1 distance. Okay, maybe that's possible, all right? But that will be it. Okay, good. So how am I going to do it? How am I going to do it? Okay. I can even tell you in advance, I will design the final distance metric in such a way that, there exists a nearest neighbor in your data set, okay? And the distance from Q to that nearest neighbor is 1. And then if this is the case, I also have to define, this is only part of the story, right? Because, I also have to construct the distance values from Q to all the other points, right? So if this P is not P star, and then you know what? I will make it 1 plus 2 epsilon again. Okay, 1 plus 2 epsilon again. So I can even tell you this is what's going to happen in the end. Okay, in the end, I won't lie. Definitely, I won't lie. I even tell you this. Okay, so if you look at this, what's the rationale behind? The rationale behind is clearly, this P star is the only possible 1 plus epsilon a and n. You see what I'm saying? Because by definition, if you give me another point, and then I expect to see that the distance should be at most 1 plus epsilon times the exact nearest distance, right? So it can be no more than 1 plus epsilon. That's why I put this 2 here. Okay. All right. So basically, I force you to find me the exact nearest neighbor. Okay. All right. Good. And furthermore, I have to play by the book, meaning that this distance function ought to be a metric. You see what I'm saying? It has to satisfy triangle inequality. Okay. Does it satisfy triangle inequality? Obviously, yes, right? You just, do case-by-case analysis, let's say 3 points, and these 3 points do not involve Q, and then you always have, 3 distances, right, from small to big, right? 1 plus 2 epsilon, 1 plus 2 epsilon, 1 plus epsilon. Okay, all good, right? Well, if you involve some Q, and then, basically, in the worst case, you will have 1, and then 1 plus 2 epsilon, 1 plus 2 epsilon, right? And again, the triangle inequality is respected. Good, all right. Now, the thing, well, where is the catch? The catch is you have no idea which one is my P star. You see what I'm saying? I promise you that eventually, when I reveal which one is P star, it's going to look something like this, okay? But the thing is, I don't promise you which one is Q star, okay? So if you think about it, you have no idea about what is the final distance function. Okay, so if you think about it, this distance function really depends on my choice of P star, right? And my P star, I have n choices there, right? Any one of them could be my final P star, okay? So basically, conceptually, I'm holding in my hands, or I have a pool of distance functions that I can choose from. And then my choice will depend on how you react. You see what I'm saying? Okay. All right, now let's play. You have your data structure, right? Okay, good. So run it. All right, so now I have the query. Now remember, for the query, you don't see anything. You see what I'm saying? In metric space, there's no coordinate for you to see. Okay, all you can do to get information about the query is to evaluate distances. You see what I'm saying? So basically, your interaction with me will be like, I'm waiting for you to ask me what is the distance from query, which is the Q that I said I have. And then you give me a data point P, right? And then you request a distance evaluation. You see what I'm saying? You request a distance evaluation. And your distance evaluation always involves Q, because if P1 and P2, you have already seen this in pre-processing, right? You don't have to ask me, right? You have already got that for free. Good. And now let's play, right? So very easy. So at any moment, I keep track of, let's say, P sim. All right, so this is a big P sim. Okay, so this P sim is the set of points that you have asked me about before. You see what I'm saying? Okay, so in the beginning, this is empty, right? I'm just sitting here. I wait for you to ask me, for distance. Okay, so you say, okay, here is P1, and then I put P1 into this P sim. Okay, and then I give you back a distance function. Distance value. Okay. Now my strategy is very simple. Okay. So if you give me something not in P sim, okay, and then I calculate how many distance values you have requested You see what I'm saying? Basically, this is the size of P sin. You see what I'm saying? And if the P sin size is less than or equal to n minus 2, because my goal is to force you to do n minus 1 distance computations, right? So if you have computed no more than n minus 2, then I'm going to return, you know what? This is 1 plus. So that's much. All right, feel free to ask me whatever you want, right? So what is the distance? Always 1 plus 2 epsilon, 1 plus 2 epsilon, 1 plus 2 epsilon, all the way until you have calculated m minus 1 distances. Sorry, m minus 2. Okay, so if actually, you know what? I will tell you, I will do this even if you have asked, even if, okay. M minus 2, right? So now if this condition gets violated, it means that you have already calculated how many? M minus 1, right? And then I will be honest. Okay, now I say, okay, you know what? This is my P star. Okay, so this is the strategy. Okay, this is the strategy. Okay. So as you can see in the whole process, I didn't lie. I didn't lie, right? Because my duty is to offer a distance function that plays by the book. Okay, and indeed, right? I told you eventually it's going to look like this, and this is indeed honoring my pledge, right? It's just that the distance function is not fixed in advance. This is called an adversarial argument, right? So you can think about the whole thing as saying, because I want to make sure that your algorithm will look bad. So I have a pool of choices here in the beginning. Okay, so this is a very typical way to prove lower bounds. Okay, and then I observe how your algorithm behaves. Okay, so if your algorithm behaves, if your algorithm has asked for a distance with respect to a certain point, and then I will eliminate a distance function from my pool. Okay, so you keep going like this, and then eventually, there is only one distance function left, and that's the one that I will return, right? So in fact, if you already knew in the beginning that eventually it's going to look like this, you are not going to ask me for n distances. You know what I'm saying? Because according to this model, after getting n minus 1 distances, you see that all of them are 1 plus 2 epsilon. You are not going to be, I'm sure you will be smart enough to skip on the last distance, right? Because the last distance will have to be 1, right? So that will have to be P star. So therefore, no matter how smart you are, you will have to ask n minus 1, and n minus 1 is already the best you can do under this model. Okay. All right, so now I have constructed a hard instance, right? I have proven that no matter what your algorithm is, the best query time on this particular data set is n minus 1. Okay, so now we can try to relate this to the bounds of disk ANN, okay, to see what happens there, right? You can see this ANN seems to be very efficient, right? You can see the query time is very, very small, right? It appears to be very small because it's log and then 1 over epsilon to the power of lambda, right? But now you realize, there's this lambda thing that potentially this lambda thing is big for the data set that I have given you, right? Indeed, the most important thing, of course, I didn't cheat, but the most important thing is to make this lambda large, okay? So now, since you have already understood the distance metric, right? And also this M, right? So you have the whole metric space here already defined. You are in a position to analyze what's the doubling dimension. Okay, so I will skip this analysis because I think this is a pretty easy for you. And I'm sure you can take time to figure that out, right? But if you look at it, you will see that this 2 to the power of lambda. So basically, this is saying if you have a ball of radius r, right? So how many how many balls of half the radius will be needed to cover that ball, right? You have to maximize this, and you will see that this is at least n-1. So in other words, the dimension here, the doubling dimension here is at least basically log n. Okay, so almost log n, right? So this is something very large. Okay. Well, now remember, if I do this, right? So I forgot to mention, let's say you set epsilon to be something less than 1/2, and this argument will work. Now think about epsilon being 1/2, right? Now, interestingly, this is saying something more than just n-1 being necessary. You understand what I'm saying? Suppose this is saying, 1/epsilon to the power of lambda -1 is necessary. You see what I'm saying? For example, if some of you dare to claim that you have another algorithm that can do 1/epsilon to the power of lambda/2, you improve this power on lambda by half. Okay, lambda/2. All right, so maybe, I don't care, you might have log n or log square n or even root n, something like this, right? If some of you some of you told me that, this would be your query bound, and this is some query bound that you can guarantee, regardless of how much space you need. You must be a liar. Why? Think about it, right? So in the scenario that I constructed, right? So the value of lambda is, as you know, right? So at least log base 2 of n-1, and epsilon is 1/2, right? And therefore, this term of how much? Roughly root n. But this is a contradiction because I told you before, right? No matter how smart you are for this particular data set, you have to evaluate at least n-1 distances. And therefore, there is a contradiction. You see what I'm saying? And therefore, as you can see, right? So this term, this 1/epsilon to the power of lambda is basically necessary. This is another very important implication of this construction. Okay. So next time when you see something like this, I think this term really deserves some respect from us. This is not just some arbitrary term there that has to be there because we're not smart enough. Okay, this is something that must be there. Okay, good. Well, so this is the first thing I want to talk about, right? So now you get to understand the role played by the doubling dimension. All right, so this doubling dimension not only allows us to analyze the performance of an algorithm, also it plays some very key role in characterizing the difficulty of this particular ANN search problem that you are looking at, right? As you can see, lambda can go from 1 all the way to log n. It cannot go over log n, by the way. Okay, so 1 all the way to log n, right? So this spectrum is a huge spectrum. You see what I'm saying? All right. So basically, it serves as one way to measure how difficult this particular problem instance is. Okay. All right. So if this sounds good to you, let's move on. Okay. So let's move on. So now let's accept the fact that lambda is something small. Okay. Now let's ask another question. Now this time it becomes much more practical. Okay. In fact, this is a question that many papers have been trying to address. Okay, look, let's take another look at for example, the space consumption. Okay, so if lambda is small and epsilon is small, so this term is pretty small, right? So for the rest of our discussion, let's just say that epsilon is 1 and lambda is 1. All right, so we look at this particular case, right? So that this 1/epsilon to the power of lambda, this term seems to be small, right? Okay. By the way, for practical use, right, oftentimes this value of epsilon would be the constant in practice, right? So for example, epsilon being 1, that would be something useful already, okay? And lambda, as I said, this has to be also small, right? So that you can have a plausible explanation. But today we're talking about lower bound, okay? I'm trying to make some points very different from the upper bounds, okay? Look, for the lower bound purpose, let's make it easy for you because this is not going to affect the question that I'm going to ask. So I say epsilon being 1 and lambda being 1. Okay, so basically I'm saying you forget about this term, right? Now, oh, the space, yes. Okay, so now you can see, actually this is not square, right? I think this square is a mistake, right? I think I proved before that this is log delta. It's just the query time. It has a log squared there, right? Okay, so this is a mistake from earlier, okay? All right, so now if you look at the space consumption of disk A and N, right? So you can see it's N times log delta, right? So if you accept the fact that it's 1 over epsilon to the power of lambda is something compulsory, and let's get that term out of the picture by assuming epsilon being 1 and lambda being 1. So this is a very, very specific case for you, right? So the point is, it's N times log delta, right? And in industry, people do not like nonlinear space. You see what I'm saying? Okay, N times log delta, that's going to raise some eyebrows. All right. So if let's say if you propose something like N times log delta and you go to industry or go to Sigma or VLDB, right? So normally a question that you will get is nonlinear. Okay, it's nonlinear, right? Is that right? Okay. So the next question is, you know what? I want you to design a linear space proximity graph so that you can beat disk A and N, right? Sounds like a very reasonable request to kill the paper if you think about it, right? Okay, cool. Today I'm going to show you this is not possible. Okay, even if epsilon is 1 and lambda is 1. Okay, it's not possible. If someone promises you that the proximity graph has linear number of edges, okay? I don't even care about query time, by the way. Your query time can be as bad as sequential scan. It just has to be a 1 plus epsilon proximity graph. Basically says that it has to be correct. I'm going to show you that any proximity graph will have to use N times log delta space. It must have that many edges. Okay, if someone claims in a paper that the space is always linear, it must be a lie, or it must be, a temporary observation from some limited number of experiments. You see what I'm saying? All right. From a theoretical perspective, it's simply not possible to have a proximity graph with N log with linear number of edges. I will prove to you N log delta is already optimal in the worst case. All right. So the lower bound proof is not trivial. Okay, it's not trivial. So I'm going to actually present an easier lower bound first, right? But so that you can get an idea why this is true, okay? And then see how much time we still have, and then I will see how much I will talk about the final lower bound, okay? Although in the lecture notes I have the strong lower bound presented, okay? So as I said, for the subsequent discussion, I'm going to focus on a very easy scenario, right? Epsilon being 1, so 1 over epsilon is just 1, okay? You cannot ask for more than that, right? Okay, so lambda is 1. So basically, this seems to be a very easy metric space. You see what I'm saying, right? So this is sort of like one-dimensional, okay? Except, it's metric space, right? Okay. All right. So today, I will first prove to you that, this n log n, so every 1 plus epsilon pg, so basically 2 pg, right? 2, right? Epsilon is 1, right? Must have n log n edges. Okay, n log n, right? So n log n is not as good as n log delta because delta can go crazy, right? So the strong lower bound says, yes, if lambda is crazy, the delta aspect ratio. If delta is crazy, I said lambda, right? So terrible mistake. Lambda is 1, okay? So if delta is crazy, and then n log delta can be much more than n log n. You see what I'm saying? Delta can even be 2 to the power of n. You see what I'm saying? All right, so n log delta is going to be n squared. Indeed, n squared would be necessary if that was the case. This is something we'll hopefully get to talk about later. All right. So this lower bound simply is something much weaker. So it says n log n. But this is powerful enough to, refute all the claims that you can have a linear size PG, right? Even it's two PG. You see what I'm saying? Okay. All right, so for this purpose, I have to construct a hard input again, right? So one hard input, it goes against all methods, right? Okay, now please watch carefully how I'm going to construct this hard input, all right? So I'm going to have a, so you first give me any power of 2. I will use that as the value of n. Okay, so basically, again, for every n, there is a hard input waiting for you there. Okay, so the hard input goes like this. So first of all, I will construct a perfect binary tree. Okay, not binary search tree. Okay, so just the binary tree. Okay, so this binary tree is perfect in the sense that all the leaves are at the same level and every internal node has 2 children. Okay, perfect. Okay, perfect. Now, I will have n leaves here. Okay, n leaves, right? So if you look at the number of levels, so if I define, let's say h to be log base 2 of n, and then you have exactly h plus 1 levels, right? So this is level 0, this is level 1, and all the way up, and the root is standing at level h plus 1. You see what I'm saying? Okay, all right, good. Now, I have to tell you M and D, right? M and D, I have to construct a matrix space, which I claim to be hard, right? Okay, now this is not something easy at all, okay? So I'm going to construct this M to be just, the set of leaves. All the leaves there, so they form a set, okay? So all these leaves, right? When I say a point, I'm actually just talking about a leaf node, right? And you cannot take any internal node because internal node is not in M. You see what I'm saying? All right, so I'm designing a matrix space, right? Good. But I still have to tell you the distance function, right? That's trickier. That's trickier. Okay. Now for this purpose, I'm going to put weights on the edges of the perfect binary tree. Okay, so how am I going to do this? Well, if this is a leaf, and then I look at its parent. All right, so there's an edge over there, right? So this edge, its weight is 1. Okay, so basically between level 0 and level 1, every edge carries the weight of 1. Okay. All right, so this might look a little bizarre to you at this moment, but if you go up one more level, right? So basically this is level 1, an edge between level 1 and level 2, right? So what's the weight? Some of you would say 2. No, still 1. Okay, still 1. But you will see the point later. All right. Now, if you go one level up, yeah, now it starts to double. All right, so now this is 2. Okay, by the way, this is not so weird at this point because 1 plus 1 plus 2, hey, that's a power of 2, right? 1 plus 1, that's 2. Hey, again, that's a power of 2. How about 1 itself? Oh, again, a power of 2, right? So that's why 2, 1, so that you can, add basically one path up, and that's always going to be a power of 2. So that's going to make it a lot easier, okay? Now, if you go up one more level, and then the weight that I put there will be 4. All right, so actually from this point on, okay, it always doubles. You see what I'm saying? Okay, good. Well, if you want something more general, then you can talk about level I, level J, and you can define that that's something some power of 2 that depends on the level, right? So this is the edge weights. Okay, good. Now I'm ready to talk about the distance function, right? So now you take 2 leaf nodes. Okay, so these are leaf nodes, right? So these guys are from M, right? So that's basically telling you, these are leaf nodes in the tree, right? Good. Now, what I want you to do is look at the LCA of U and V. Okay, LCA, right? So you understand what LCA is. Let's say this is U, and this is V. LCA, lowest common ancestor, right? Lowest common ancestor in the tree. This is let's say this is the LCA, right? Okay, so if you have this LCA here, right, and then you will see that this LCA has some very nice property. So I will talk about that property later. But I just realized in order to define the distance, I don't really need the LCA. So I'll come back to the LCA later. So I will define this DUV as, the distance of the shortest path between U and E. You see what I'm saying? Okay. So if you have got two leaves here, what would be the shortest path? Okay, what would be the shortest path? There's no way else you can go, right? You have to go up to your LCA, right? And then go down, right? So you don't want to go up, oops, and then back down. And then no, that's not going to be a shortest path, right? So if you do this, right? So this is basically saying, you are going to arrive at the LCA and then go back down, right? Good. So by the way that we design this distance function, there's one very nice way to calculate this, right? So you simply look at the level L here. What is the level, right? And now we start counting from 0. You see what I'm saying? We start counting from 0. So you can do the math and you can realize that there's something very, very convenient here. This is simply 2 to the power of L. Okay, so it depends on which level your LCA is gonna be. And then the distance is precisely 2 to the power of that level. Okay, well, let's have some quick examples. Oh, by the way, I forgot to mention U and V, of course, will have to be different, right? Because if they were the same, we are obliged to say the distance is 0, right? So there's no other way around it, right? So this is the self-identity property, right, of this metric space. All right, now let's say if U and V, this L is 1, right? So basically 2 leaves and their parent is right above them. Okay, if this is the case, you can see 1 plus 1. Hey, that's 2, right? So 2 to the power of 1. We're correct, right? Now another example, if this W is at level 2, and then basically 1, 1, that's already 2, and then 1, 1, so that's 4, right? Hey, 2 to the power of L again is correct, right? Well, if you don't believe me, you can try more examples, but I'm pretty sure I'm correct here. Okay, all right, cool. So this is the distance function. All right. And there you go. I have the metric space for you. Now this time, I don't even play tricks by saying, I will hide my distance function. Okay, so the distance function is right here. Okay, so this M is already right here. The whole metric space is exposed out front. You see what I'm saying? Like you can do whatever you want. Okay, now go ahead and compute a proximity graph and come back and tell me how many edges you have. Well, if any one of you says you have less than n log n, okay, I don't believe you. Okay, all right. So now here's the interesting thing, right? So I claim that this is a hard instance, but I have to prove it, right? So eventually I will be able to prove to you that, oh, by the way, what is P? I forgot to mention P, right? Well, P is just M. You see what I'm saying? P is just M. Right, so every point in the metric space will be presented as a data point. Now, what is Q? Q comes from one of the leaves. You see what I'm saying? All right. So if you think about the mathematical definition, everything sounds perfect. Okay. Very nice. Okay, so this is the metric space. All right. So eventually, I will prove to you that in your graph, okay, if your graph has to be a 1 plus epsilon PG, so that means 2 PG. Okay, 2 PG, and then every point or leaf, right? Point and leaf, they are the same thing, right? Every point must have log n out neighbors at the order of log n out neighbors. Okay, every single point. All right, if that's not the case for you, something must have been wrong. Okay. All right. Well, if you are ready, then I'm going to present the argument. Okay. Well, this requires something that goes all the way back to the first seminar. Okay, so here is an excellent moment for you to appreciate a concept and also an if and only if condition that I proved in the first seminar, right? Because I know that your graph has to be 2 PG, right? But if this 2 PG is the only thing I can rely on, then things go really, really complicated, right? Because I don't know where to start, right? Because I don't really have another very handy property that I can utilize, right? So 2 PG basically says, you always have to return to approximate nearest neighbor, but that's not good enough, okay? However, in the first lecture, I proved something called 1 plus epsilon, which is 2, right? 2 navigability. You see what I'm saying? 2 navigability. I don't know if you still remember that, which is okay. All right. And then let's review this 2 navigability together. Okay. So this 2 navigability basically says, right? So you take any P. So this P is in the data set, right? And then any Q is from the metric space. Of course, here P and M are the same, right? So it says either P is a 2 nearest neighbor of Q, which means, imagine if you were standing at P, right? You could return just P itself, okay? So it doesn't have to do any more greedy. Or if P is not good enough, or P has an out neighbor, let's call it P out, such that the distance between P out and Q is strictly less than the distance of P and Q. See what I'm saying? So this basically says if you yourself is not returnable, and then some out neighbor can strictly improve you, right? So this is 2 navigability, right? So very importantly, we proved an if and only if condition in the first seminar, right? So if you call your graph a 2PG, it must be 2 navigable, okay? And personally, if your graph is 2 navigable, it has to be 2PG. You see what I'm saying? Okay, good. Now, this is the property that we will utilize, because this is much more useful if you think about it, right? Much easier to check and use, right? Good. All right, so now I'm going to make the claim, right? So this claim says omega log n. Log n is the height, okay? Now use the action later. Log n our neighbors, no matter what. I don't even care about the current time of your proximity graph. Actually, the proximity graph itself doesn't really require current time to be small. You see what I'm saying? It has to be correct only, right? So this is the claim, all right? So not a trivial claim to prove, but I'll prove it, okay? So if I manage to prove this, and then n log n is already a lower bound, all right? Because every out neighbor consumes 1 edge, right? Okay, good. Now the thing is why this is true, okay? Why this is true. All right, now let's see. Well, I say feel free to pick whatever leaf, okay? So let's say P, okay? So this is the leaf you pick. Okay, and then I say, good, now I'm going to take over from here, okay? And then I'm gonna argue that this P must have log n at the order, okay? Log n our neighbors, okay? Well, I'm going to look at the tree. Now, still remember, I've got this tree here, right? This green tree, perfect binary, okay? So I trace back up all the way to the root, is what I'm saying, okay? So if I do that, sometimes I make a right turn, just like here, right? And sometimes I make a left turn from the parent, just like here, and basically it's a zigzag. Oh, yeah, there you go. Okay. All right, so that's the root. Okay, so that is the root. All right. So so this root to this P, as you can see, how many edges there are there? Exactly H edges. Okay, H edges. Good. Now I'm going to define a notion called off-hanging subtree. Okay, off-hanging. Hey, that sounds cute. Off-hanging. Okay, now what do I mean by off-hanging? Look, here, this is a path already, right? This is a path. Wait a minute, just move this up a little bit so that you can see better, okay? All right, now you can see I go from the root and I go down. As I said, sometimes I make a left turn, sometimes I make a right turn, right? So every time you make a left turn, take the right subtree of your current node. So that's sort of like an off-hanging subtree, right? So it's a subtree that hangs on the path, except that it's not on the path, it's off. You see what I'm saying? So this is an off-hanging subtree. Okay. Of course, symmetrically, right? So if you turn right, for example, if you are here, right? So the second node on the path, and then the off-hanging subtree of that guy will be this. Okay. So clearly, since you have H edges, you have H ancestors out there, how many off-hanging subtrees do you have? You have precisely H off-hanging subtrees. Cool? All right, good, very nice. Very nice. I argue you must have an outneighbor in every off-hanging subtree. Okay, all right. Thank you for agreeing with me. Okay, so early, seems that you have a lot of faith in me, right? I like that. I like that. Okay, but I still have to provide a proof. You see what I'm saying? The proof says you have H hanging subtrees here, and I argue that in every off-hanging subtree, one of the leaves there will have to be your outneighbor. If that is the case, then I complete my story, right? Because I have H hanging subtrees there. So basically, I'm saying the outneighbor of this guy would have to be H, no matter what. Okay. So you have, this holds on every single leaf, right? So in total, you must have n times H leaves. And that's n log n, right? Good. Well, let's just say that somebody wants to be my adversary. Okay, so somebody says, no way, I have a beautiful idea. So this idea says no, right? So let's say you take any node on the path, right? So it doesn't have to be the root. So that's why I draw it here, right? So you could have some more stuff up there. So without loss of generality, let's say at this node, at this internal node, we make a left turn. Is that okay, right? So that should be fine, right? Okay, so this is not an off-hanging subtree, as you can see, right? Not an off-hanging subtree. So your P is somewhere here. Is that all right? Okay. So somebody, wants to be my adversary, and you say, you know what? I have a beautiful idea saying, my graph has no outneighbor for this guy P, right? So in this off-hanging subtree, you see what I'm saying? If you compare these two figures, you can see that this blue node can be any ancestor here, and this will make sense. Okay, good. All right, so and then I come in, I say, let's look at the following argument. Okay, see what happens, right? Good. All right, so if you have no outneighbor here, and then I just pick my query point right there. All right, so let's say this is the query point. Let's make it black. Right, you see this is an off-hanging subtree, right? It cannot be empty. You see what I'm saying? No off-hanging subtree can be empty, right? So I can comfortably pick a query point there. And there must be at least one query point out there, right? Okay, good. And then I will check this two navigability requirement with respect to P and Q. And I argue that you must have violated this two navigability. And because this is if and only if, right? So it means that your graph cannot be 2PG. All right, so that's a contradiction, right? Okay, good. Now, why is this true? Why is this true, right? So first of all, what is P star, by the way? What is P star? Now, remember, P is just M, right? So Q is just a leaf. And Q itself, Q itself is in the data set. You see what I'm saying? So P star is just Q. You see what I'm saying? Okay, so P star is Q. All right, so what is the nearest distance, by the way, guys? The nearest distance is 2Q to P star. Okay, so that's point to itself. You see what I'm saying? That's 0. Okay, that's 0. You see what I'm saying? Good. And this epsilon is 1, right? So who can be a 1 plus epsilon, which means 2 ANN of this Q? Who? Just Q itself, nobody else. You see what I'm saying? Because everybody else will have a positive right, distance. Well, in general, right, if the query point coincides with the data point, right, the distance is always 0, and every 1 plus epsilon PG is supposed to find the exact nearest neighbor, right? No question asked, right? Good. And therefore, P cannot be a 2 ANN, as I said, right? Okay, so according to the 2 navigability requirement, well, since you are not good enough, somebody better improve you, right? And this person will have to be an out neighbor of you, okay? Good. All right, you have to find me this out neighbor. So you say, you know what? Yes, you do have an out neighbor. I say, give me that out neighbor. And you will say, okay, you know what? This is P plus out. Okay, out indicates it must be an out neighbor, and plus indicates this is the best out neighbor you can find. Okay, all right, good. All right, good. Let's take a look at it. So the next question I'm going to ask is, where is it? Where is it? Where is this out neighbor, right? So first of all, it cannot be in the rest subtree, right? Because you told me there's no out neighbor here in the off-hanging subtree, right? So this is the one. Good. So if it's not in here, then there are only 2 possibilities, right? One possibility is inside the green subtree, okay? Or it's outside the subtree of the parent. You see what I'm saying? All right, so only 2 possibilities. You see what I mean? Like outside, somewhere else. I don't know where that is, right? So either here or somewhere else, right? You see what I'm saying? Okay, you know what? I will draw the whole picture so that you can have an idea. You see what I'm saying? So either in this green or it will have to be outside, right? Outside basically means here. You see what I'm saying? Either green or the outside, but it cannot be inside the red, right? Well, I'm going to reject both possibilities. Okay, now remember, this P star, our neighbor, will have to strictly improve P. All right, strictly improve P. Now let's calculate the distance between P and Q. I told you before, the way that the distance, the edge weights, okay, are designed, gives a very convenient way to calculate the distance, right? So all you have to say is, what is the level of this guy? Let's say that the level is L. Okay, so you already know that the distance between P and Q, that's how much? 2 to the power of L. Okay, good. Now let's reject the first possibility first. Okay, so let's say if you tell me that this P plus L, your best L neighbor, right, is in the green subtree, right? And then what is the distance from this P plus L to Q? Well, you can see what is the LCA of this P plus L and Q if it's right here in the green subtree, right? Same guy, right? Let's give this guy a name. Let's say U, right? So if this P plus L is also in the green subtree, and then the LCA between basically any point in the green subtree and this Q will always be U. You see what I'm saying? And then it will be 2 to the power of L, right? But hey, that's not okay. You see what I'm saying? That's not okay because I'm expecting strict improvement. And that's the definition of 1 plus epsilon PG, right? So if that's not possible, the only possibility is, for this P plus L, we have to fall on the black area. But that's even worse. Yeah. That's even worse, right? Because if this P plus L was here, right? And then the LCA will be higher than level L. You see what I'm saying? And then your distance is actually worse than you. I mean, what's going on here, right? Okay, so you can see we have rejected both possibilities. So this implies that this P must have an out neighbor in this off-hanging subtree. And therefore, n log n is the minimum. Okay. By the way, if you calculate this, delta, so delta is at the level of n, okay? At the level of n, if you think about it, right? So n log delta turns out to be optimal in this case, right? Because that's just n log n, okay? So now, again, I think if you look at the bound achieved by this ANN, right? So as I said, it invites a lot of criticism, right? Oh, this 1 over epsilon thing, and also this log delta. And now I believe they deserve more respect, right? So even if epsilon is 1 and lambda is 1, oh, I forgot to explain lambda. Okay, this is something I would not prove officially here, but you can check for yourself. What is the doubling dimension of this distance metric? Interestingly, it's 1. Okay, it's 1. So every ball can be covered by 2 balls half the radius. Okay, so lambda is 1. All right, so epsilon is 1. Right. So you can see this n log delta is already the optimal in this particular case. So I've been talking for 1 hour, and I believe I have given you a main idea of how a lower bound is proved on the space of a proximity graph, right? So I won't go through the whole proof for the strong lower bound, but I'm going to quickly tell you the idea, right? So basically, the idea is the same, except that you want to do n log delta, so you cannot really have just a binary tree with n leaves. Okay, you will have to do something more clever. Okay, so I will quickly go through the proof, and we should be out of here in another 10 minutes. Okay, much earlier than last time. Right? Okay, so let's play the game. So the game is still this, all right? So this time you fix any powers of 2 of them. All right, so one of them is n, and the other one is delta. Okay, so so this delta is going to be an integer with me, and then I'm going to construct a Hartle instance. So this Hartle instance, its number of points is at the order of n, and also the aspect ratio is precisely what you tell me. Okay, so this is the thing. By the way, to prove a lower bound, this is very important. You cannot say, oh, for a particular value of n, there's some Hartle instance. This doesn't make sense. Because if you specify this n to be any finite value, that's just a constant. You see what I'm saying? You have to show for any input size, there is a Hartle instance sitting there waiting to haunt you. You see what I'm saying? This is basically the methodology. Okay. So my requirement for you is, n cannot be too small, otherwise it doesn't make any sense. N at least 2, right? Otherwise, 0 distance. I mean, the nearest neighbor would have to be that guy, right? Now this is fair, and another thing I need is, n squared will have to be less than or equal to 2 delta, and 2 delta will have to be bounded by 2 to the power. So this gives you basically a lot of choices, right? In particular, some of you, I think, asked earlier, delta can be huge indeed, right? Delta can indeed be huge. Let's say delta can, be exponential to n, right? To the power of n, basically to the power of n minus 1, right? So if you calculate log delta, yes, log delta is going to be what? It's going to be n. So log delta may not be necessarily small if delta is large, right? Okay. So I'm going to keep the promise. I will still set epsilon to be 1 and lambda to be 1. Okay, so I'm not really playing tricks with this lambda. All right, so lambda is small, so the matrix space is actually a very easy matrix space. Okay. However, we will prove that n log delta is a lower bound. Okay, this is a lower bound. Before it was n log n, and this one is much, much stronger. Okay. Now let me tell you why this is stronger. It would be very easy to convince you that this is a lot stronger. Think about what happens when delta is 2 to the power of n minus 1, okay, at that level. If that is the case, what is log delta? Well, log delta essentially is just n. You see what I'm saying? It's at the order of n. So this is telling you n squared is the best you can do. You see what I'm saying? This is telling you n squared is the best you can do if delta is that large. This is also informative. You see what I'm saying? This is also interesting because we know there is one universal way to construct a PG. The complete graph, you see what I'm saying? So even the complete graph is already optimal if delta is horrible. All right, so this is actually, very powerful if you think about it, right? So this log delta could be conceiving because it looks so innocent and small, right? But it could actually be big if delta is large. Okay, good. So I will present the basic ideas. Okay, so basically I will present the Hartle instance, and also I will present some intermediate results, claims, and then the proofs. The proof ideas are very similar to what I presented with a simpler example, and everything is detailed in the lecture notes. Okay. So this time, again, I will construct a perfect binary tree. Okay, except that this, binary tree is going to have more than n leaves. Okay, how many leaves? Two delta. Okay, 2 delta leaves. Okay, good. And I still designed the way, so edge way, right? In the same way as before, because that's very convenient if you think about it, right? So once again, what is the design? It's like, one. So that's one, and then another level, again, one, another level. Now we start to double, right? So 2, and then 4, and then 8, etc., right? But just so you know, in general, if you take any 2 leaves, right? So if you look at DUV, now this is something I told you before, this is 2 to the power of L. And this L, what is this L? L is the level of the LCA, right? So level of LCA, the LCA of UMV. Okay. Now, how do we name the levels? Leaves level 0. Okay, and then 1, 2, 3, 4, all the way up. Okay. So if I look at the high is H, and this high is clearly log delta. You see what I'm saying? Okay. So you can do the math, and then you can see this log n is bounded by H by 2. Okay, because I have these inequalities here, right? So you can do the math, and then log n is bounded by H by 2. Good. All right. So what is the matrix space? So the matrix space M, okay, is simply all the leaves, just like before. Okay. And the distance metric I have already defined, basically. Once again, everything exposed. Okay, everything exposed. Okay. Now, I will give you P. Okay, now P is defined with much more here. Okay, much more here. So I'm going to define this P. Okay. Now, I want you to look at the leftmost path of this tree, right? So this leftmost path, right? So this is the root of everybody, right? So I will, denote it as UH. Okay, H indicates which level, right? And then as you go down, I have U H minus 1. You see what I'm saying? Okay, so get used to the notation, right? So if you go all the way down, I have every node at each level. By the way, this is the leftmost path. So I'm using this curvy line here because I don't want you to think that there are only 3 levels, right? So there are many levels there. Okay, so I stop at this 1 plus h over 2. 1 plus h over 2. Well, to be rigorous, I have to put the floor because h could be an odd number and all that. Okay, so so far so good, right? But I still have more stuff going on there, right? So this will be, another few levels skipped. Okay, and then I can come down to u log n. You see what I'm saying? N is the power of 2, right? So log n is just some number. And then, this is fine because log n, as you can see, is always less than h over 2, but it could be much less than h over 2, right? So possibly you'll be skipping some levels there. Good. Now, if you look at this, I'm going to look at the subtree now. So this guy has a subtree. By the way, how many nodes are there in the subtree? Precisely n. N points. That's promising. Okay. All right. Now I'm going to look at the first basically h over 2 points. Okay, for h over 2 points there. Or I should say nodes. I think I slipped out the word point, right? Horrible mistake, right? Because these are not points. These are just nodes. Points are the leaves. You see what I'm saying? Okay, the internal nodes, they are not in the matrix space, okay? All right, so here I look at this subtree. There's one subtree there. And here there's another subtree. And all the way down. And so this is not very nice. Okay, good. So how many subtrees are there? So you have h over 2 subtrees. Okay. All right, so far so good, right? I haven't really specified anything about P yet. I'm just saying you've got n points down here, and I will be taking, the first h by 2 off-hanging subtrees, basically, right? And you might have some more subtrees here for me to use, but I won't bother. Okay, that's what's going on, right? All right, so now P. You know what? Let's get this thing away. Okay. All right, so now I'm going to construct P, right? So P includes 2 parts, okay? Everything here, P1, okay? So these n points, they constitute a set. I want all of them. So that's P1, okay, set P1. And then from these H/2 subtrees, we will pick exactly 1 point from every subtree. Okay, so I will call this set P2. All right, P2 is very small. Well, usually it's very small because it's H/2. That's basically at the order of log delta. You see what I'm saying? Okay. All right, so I've got H/2 points here, right? So what is P? P is the union of P1 and P2. All right. So the size of P is not exactly n, but you can prove that the size of P, this is precisely n plus H/2 floor. So you can prove that this is at most 3n/2, right? So it's not precisely n, but essentially n. You see what I'm saying? Okay, at the order of n. Okay, this is the Hartley instance. This is the Hartley instance. And then I say, go ahead, construct your graph. If anyone can show me it's only n log n, tell me. You must be wrong. Okay, so I can prove to you that this is the Hartley instance, and if you look at any point, okay, let any point from P1, okay, so let's say this is a guy P, okay, any point from P1, okay, so this P, all right, coming from set P1, this P, I can prove to you that each of the guys in set P2 must be an out neighbor of this P, okay? Once again, you must have an out edge from P to this black point over here, P to this black point over here, this P to this black point over here. Okay, I don't care whether you have out neighbors within the set P1, right? But if that is the case, you can see this P must have an out neighbor. How many out neighbors? Log delta, because that's H/2, right? H/2 is at the order of log delta, right? And therefore, in total, you must have at least how many edges? N times log delta. Okay. All right, so I will not go into the proof further, but the main idea is pretty much the same. All right, so suppose you challenge me and you tell me, oh, this P does not have an out edge to, let's say, this guy here. Okay, so let's say this guy, right? So I'm recording the video. Let's say this guy here. Okay, and then you will prove something's going to go wrong, right? So I've just placed my Q here. Basically, same argument again, right? I placed my Q here, okay, and I argue you cannot be too navigable. You see what I'm saying? All right, so that's everything I have. I hope to see you next week.